Good morning. Today we are looking at the theory of relativity. The theory of relativity at its foundation is a description of how space and time components are interconnected. And what it's going to lead to for us is a more reliable set of formulas so that we can determine energies and momentum and such. So anyway, let's get started with this. There's a list of topics within the chapter, and let's go ahead and get started. So relativity did not start with Einstein. There was classical relativity that dates back to Galilei and Newton, and the idea is that you could have coordinate systems, and those coordinate systems could be have a relative velocity between them. So I could have a coordinate system sitting here, standing at rest in this coordinate system, but I could also be in a train, moving along at a constant velocity. And if I'm in a train at a constant velocity, the physics inside that train works the same way that it does in any other inertial reference frame. So as long as these reference frames are not accelerating, then they are inertial reference frames, and the formulas that we've developed in the course will work in any frame that is not undergoing an acceleration. So any constant velocity frame, those are going to work. So here's the idea. The idea here is if I'm in the car driving along, then in my reference frame, I'm at rest. I'm at rest within the car. The stuff that I have stacked around in my car, those items are all at rest within my car and within this reference frame. When I look outside the car, I go, oh, all these things are going by, and they're going by at some, because I'm at rest. And these other objects outside are going by at some velocity. Now, in the other reference frame, if we move over to the outside reference frame, people standing outside or objects outside, you look around, everything's at rest, and you go, well, in my reference frame, I'm at rest. And then you watch this car go by, and the car is going by at some velocity, and you go, oh, look, there's an object moving at velocity v through my reference frame. So this is an example of two reference frames. Now, as long as the objects here are moving at constant velocity, the physics works the same way in each of those reference frames. So in this reference frame, the car's reference frame, the car is at rest, the Earth is in motion. And by Earth we mean the outside, looking out at the outside stuff that we see. And in the other reference frame of the Earth, then the Earth is at rest and the car is in motion. So the inertial reference frames are going to be characterized, we say, by constant velocity. If I'm in an accelerating frame, then there are going to be effects that I notice due to that acceleration. So, for example, if I'm standing on the surface of the Earth, and we've got this person right at the equator, they're actually not in an inertial reference frame. We can calculate the acceleration that that person is undergoing, that reference frame is undergoing, based on formulas that we've developed for circular motion that show us that the acceleration of someone standing on the equator, due to the rotation of the Earth, we have not brought in orbital motion yet, but just to the rotation of the Earth, there is an acceleration of 0.0339 meters per second squared. It's not such a big deal. And so what we can do is, we've been treating, objects on the surface of the Earth, we've been treating the surface of the Earth as being an inertial reference frame. And so you can see that's been a bit of an approximation. A few times during the physics series, back maybe more in physics 4A, when we were looking at physics 3A, sorry, back in physics 3A when we were looking at gravitational fields, and accelerations. We looked at some examples of how objects were accelerating, or the effect of the acceleration of the Earth. And again, it turns out to be a fairly small effect here. All right. And so the formulas that we've developed, those are going to work as long as we're in an inertial reference frame where the reference frame is roughly undergoing constant motion, steady motion. So let's take a look at the speed of light. Now in the textbook, they spend several sections on this, and I'm going to suggest don't get bogged down with all of the details in those early sections in the textbook. If they're useful and make sense, that's fine. If you choose to just kind of bypass them at first, I think you can kind of jump in several sections in, kind of follow what we're going through in the lectures here, and still, develop all of the skills and the ideas you're going to need to be able to set up problems in this chapter and carry out the calculations. So let's look at one example here of how relativity works and kind of how relativity developed. If we were in a train, let's say we're on the BART train or something, and the train is moving. Ooh, that's really fast. So the train is moving at 100 meters per second, like 200 miles an hour or something. So I guess we're not on a BART train. Maybe we're on a bullet train or something, traveling along. And then we're throwing something back and forth. Maybe we have a baseball out and we're playing catch on the train. And when we throw it forward, it's at 10 meters per second. And when this person throws it back, it's at 10 meters per second. That's in the reference frame of the train. Now, a person outside, when the ball is going forward, would say, oh, that's 10 meters per second plus an additional 100 meters per second. That ball is going past me at 110 meters per second. Now, when the person here throws the ball back, well, in this person's reference frame, in the reference frame of the Earth's surface, that would be 100 meters per second forward. The train is still going forward at this really high speed. The ball's being thrown back, but the combined velocity forward would be 90 meters per second. So whether on the train the ball is being thrown this direction or that, in the Earth reference frame, the ball is going forward, first at 110 meters per second, and then at 90 meters per second. Now that comes from just adding velocities, and that's what we do in standard classical physics, where components of space are separate from components of time. Now, what would happen if instead of throwing a baseball back and forth, what if we send photons back and forth? What if we're sending photons forward and backwards inside this train as it moves, and then we measure them on the train, the speeds, and then we measure the speeds outside of the train? Well, on the train, we get a flashlight out and we shine these flashlights at each other, and we measure the speed at which the light's making its way through the train, and sure enough, it turns out to be the speed of light. It turns out to be c, where c is 300 million meters per second. So let's see, how have we labeled these? So we're calling this reference frame, the train, reference frame S prime, and I guess the Earth's surface is reference frame S. I just thought I would mention this notational stuff, because that gets used in the textbook, and we're going to use that in lecture 2. So here is inertial frame S with coordinate system x, y, z. Here is inertial frame S prime with coordinate system x prime, y prime, z prime. And what we've done is we've lined up the x-axis, axes between the two frames. So this is the setup that we'll work from in deriving the formulas that we derive in the chapter. And then this represents a relative velocity between the two. So we can't say this one's moving and this one's at rest, or this one's at rest. It's just a relative speed between the two. And if they're both inertial frames, then they're both moving at constant speeds relative to each other. All right, so let's get back to this example where we're sending light back and forth. Well, simple addition would say that, if the train's going 100 meters per second, then the light going forward would be traveling at c plus 100. The light would actually be traveling faster than the speed of light. And then on the way back, the light would be traveling at c minus 100. Or 100 minus, I guess c minus 100 in the backwards direction. That would be the prediction from classical physics. So classical physics would say there is one of these reference frames where light is able to travel right at c, but in the other reference frame, it's just not going to have the same velocity. That's not possible. Now, classical physics, the idea of space and time from classical physics, dates back to actually the 1600s, 1700s. In the 1800s, theories or formulas describing electric and magnetic fields were being developed, and as we know from earlier, from a few weeks ago, actually, not that long ago, we were looking at propagating electric and magnetic fields. And what we found is that within Maxwell's equations, within electric and magnetic field propagation formulas, is the prediction that they travel at a fixed definite speed. Now that seems like a contradiction, because how am I going to get the light to be traveling at the same speed in all the possible reference frames? How could light be traveling at the same speed relative to all the observers? In fact, we could make this a kind of an extreme example. Let's say that the train, instead of a super fast train at 100 meters per second, let's say it's a really super fast train going 99% of the speed of light. Now, if that train is going 99% of the speed of light, what does it feel like to go that fast? And it feels the same as being at rest, because that's how nature works. So as long as we're in an inertial frame, traveling at a fixed, constant speed, it feels the same as if you're just at rest, right? Maybe the best example of this is Earth's orbital motion. Turns out that the Earth is traveling along its orbit at about 67,000 miles an hour. Now, you would think if you were going 67,000 miles an hour, you would know that. You would feel some kind of an effect, but you don't. As long as the velocity is steady, just a relative velocity itself doesn't produce any observable effects. So traveling at 0.99 times the speed of light would just feel like you're sitting at rest. We look at galaxies, so we can look at galaxies that are separating from us at, these enormous speeds, maybe at speeds near the speed of light, and we might think, wow, I wonder what it feels like to travel at near the speed of light, and it feels just like this, because, observers from that galaxy looking at us would say, wow, that galaxy is traveling at near the speed of light. I wonder what that feels like. And it's not that remarkable. It's just the same as being at rest. Right, so that's the idea with these inertial frames. We can talk about these enormous relative speeds, but within any inertial frame, it just feels like you're at rest. It's the very same experience. So anyway, the observers on the train measuring the light are going to see it traveling at c. Now, what electromagnetic formulas from Maxwell's equations predict is that not only will these observers, but these observers too, will always see the light traveling at c. How is that possible? And let's think about what we mean when we say something is traveling at a particular velocity. Velocities are determined by measuring distances and measuring time intervals. So if there was some way that within the two reference frames, that distances and time intervals were measured to be different, that would allow the possibility that everybody is measuring light to have the same speed. And that's the approach that Einstein took. So Einstein took the approach that maybe this is really possible. Maybe it's possible that this value of c, it has the very same value in every reference frame, and that by coming up with some kind of formulas that describe how distances in the two different frames are going to be different values, and the time intervals will have different values, that the speed of light works out to be the same value for all of them. Okay. Now, often what happens with relativity is when we start talking about, well, the speed of light is the same in every reference frame, the first inclination is, oh, there's something special about light that makes it travel at the same speed in every reference frame. And it's not, relativity says that light is traveling at c because the photons are massless. So relativity predicts that first of all, relativity says you don't have to have mass to exist. Mass is not a prerequisite. And then relativity says if you happen to be massless, if you happen to be a particle that has no mass, then you will always be traveling right at c. And even if photons do have mass, let's say we've measured them very carefully, as far as we can tell they have no mass, but what if tomorrow's headlines say, scientists discover photons really do have mass? Then what we would find is that if that's the case, then the photons aren't traveling at c. They're traveling at something less than c, because c fundamentally is a conversion factor that tells us how time and space are connected. You know, what's a conversion? How many seconds of time correspond to how many meters of distance? And if particles are massless, any particle that's massless will be traveling at c, but any particle that has mass can't quite travel at c. And also, there will always be a reference frame. If a particle has mass, or if an object has mass, we can always find a reference frame where that particle or that object will be at rest. So here are some of the predictions that Einstein came up with. When Einstein developed the formulas saying how distance and time could vary between different reference frames, here's what he came up with. There's this effect called length contraction. So the length measured in one reference frame will not be the same distance measured in another. An example of this, let's say we have a meter stick at rest. So what we've done is we've gone to the meter stick factory where they're producing the meter sticks, and at the factory they hold the meter sticks up and they hold them right at rest, and they check them with the standard reference meter stick to make sure that they've made it exactly the right length, and they go, yes, inspected by, this one passes inspection. So here's the meter stick at rest. It's right at 100 centimeters. What happens though if that meter stick is now put into motion? What if the meter stick is moving along really fast? Or what if someone on one of those really fast trains, let's say there's a really fast train going at 80% of c, and they're holding a meter stick, how long will the meter stick be in our reference frame? So going back here, let's say this person has a meter stick. Well, the observers on the train get out and carefully measure the meter stick, and they can see that it's a meter long. But a person making that measurement in the other reference frame, as that meter stick is going by, in fact, the train would show this effect. Everything in that reference frame, everything in the other reference frame, would show the effects of length contraction. It would say that objects are shorter. The meter stick that was 100 centimeters in a frame where it's at rest will only be 60 centimeters long in a frame where it's moving at 80% of c. Now, 80% of c, that's a really high speed that we would need to get to see a dramatic effect like this. What happens if it's going slower? Well, the general formula for this is the length, length contraction formula says that the length, the distance that something takes up will be L naught divided by something we call gamma. And gamma is given by 1 over 1 minus v squared over c squared square rooted. That's the formula that Einstein came up with. Actually, it's a formula that Lorentz came up with before Einstein. So Einstein was apparently aware of how this conversion could work. But Einstein was the one that really became attached to the idea that space really does behave differently and time intervals really are different when measured from other reference frames. These effects are real. This is reality. And so this factor of gamma, 1 over 1 minus v squared over c to the half, what we could do is we could say, what are the properties of this mathematical gamma factor that describes the length contraction? And also it's going to describe something we call time dilations. So variations in length, variations in time. Now, this factor, let's put some numbers into the formula and see. The gamma factor, when an object is at rest, the gamma factor is 1. So it says that if an object's at rest, it's just going to be its rest length, what we've called L naught here. Also, if an object is at rest and we measure the passage of time, the time passage will match what we call the proper time. So with a velocity of 0, gamma is 1, but well, we're going to jump here pretty much to a large value here. 0.50 c, the gamma factor becomes 1.15. So we'll see a 15% effect as far as length contraction. So we'll see things 15% shorter at a speed of 1/2 c. Now, the gamma factor starts out being equal to 1 when an object's at rest. When it starts moving, the gamma function doesn't change very rapidly at first, but then it starts changing more and more rapidly, and as v approaches c, the gamma factor goes to infinity. V equals c is an asymptote for that function, and what special relativity predicts is that there's no such thing as faster than c. It's not because we don't have the propulsion systems, it's just a fundamental property of how space and time are put together. When we think about velocities as being a distance divided by a time, right? What special relativity says is that we will never measure an object traveling a distance divided by some time interval. That ratio will never be larger than c, because of the way space and time are connected. The way that space and time are connected, there's no such thing as going faster than c. So the gamma factor is defined over this allowed velocity range between 0 and c. And these are just a couple of values. We'll see more examples of calculating gamma as we go along. As v approaches c, gamma heads off to infinity. Now, along with this length contraction effect, there's also what's called a time dilation effect. Now, a good example of this is, well, there are these unstable particles. You guys are probably familiar with radioactive decay, for example, but there are these other just fundamental particles. This is a muon. It's a particle that's like a heavy version of the electron. Now, the electron is stable, but the muon is not. The muon can decay into other particles. If the muon is generated, if we generate muons in our labs, where they're just at rest, what we measure their lifetime to be, on average, is 2.20 microseconds. So it's not an especially long lifetime, right? Although for unstable particles, this is actually one of the longest lifetimes that we observe. So 2.2 microseconds as a lifetime. Well, what happens if instead of these being at rest, what if the muons are generated so that they're traveling at some speed? As they go at higher and higher speeds, what we'll find is that the muon will live, on average, the lifetime gets longer and longer. And this effect was predicted by Einstein. So Einstein made this, special relativity was developed and the formulas were published in 1905. And it really wasn't until the 1920s and 30s until researchers start to observe these particles coming in through our atmosphere and measuring their lifetimes. And what they found was muons at rest survived for 2.20 microseconds. That would be considered an example of a proper time. So we would say that's T naught. But if they're moving in our reference frame, then they might survive longer. The example of the numbers that I've put here would be a factor of 2. What if we have a gamma factor of 2? Well, then the muon would live twice as long. What would it take? What speed would be required for a factor of 2? Now, we didn't put that on our table, but it turns out a factor of 2, in terms of gamma, requires going about 87% of the speed of light. And that's not unusual for these particles. So we can pretty readily develop or produce beams of muons now. We know how to do this. And we can generate them so that they're essentially at rest, or we can generate them so that they're going at really high speeds. And as the speeds increase, we can easily verify that the time dilation formula, it just works. It really describes what's going on. Now what's interesting here is, well, what if I'm in a reference frame? Let's say we take this muon that's moving at really high speeds. In our reference frame, it survives longer, but what if I now move into a reference frame moving right along with the muon? Well, in my reference frame, the muon's at rest. And in that reference frame, the muon survives only 2.2 microseconds. Okay. So these are unusual sort of effects that we're talking about here. Length contraction and time dilation, that's just really, really surprising. But it's real. Experiments have been looking at these kind of effects now for well over 100 years. And everything we do where these kinds of calculations come up show that special relativity it just gets everything right. So anyway, let's go on and look at some examples with some of these formulas. I know it's a new set of formulas to work from. And so what you want to do is jump right in and start getting some practice with these. So again, what I'm going to say is all those early sections in the chapter, you're welcome to read through those. I'm going to say you don't necessarily have to. If you're on board with the idea that there could be these differences between lengths and times in different reference frames, then you're ready to jump in and use the formulas that special relativity provides. So let's try this. Let's say, oh, look, it's a muon and it's moving. What will be the average lifetime of a muon if it's traveling at 0.6 c? So that would be 1.80, 10 to the 8th meters per second with respect to the laboratory. Its average, its mean or average lifetime at rest is 2.20 microseconds. How far would the muon travel before decaying on average? Now, if you're familiar with radioactive decay or the decay of unstable particles, you're aware then that there's not a fixed lifetime. There's kind of a statistical distribution. Some of these particles will live longer, some will live shorter. What we're specifically referring to is the average or the mean lifetime for a muon at rest. Now, for the lifetime for unstable particles, we use the symbol tau. So I'm going to call this tau naught to say this is the proper lifetime. It's the amount of time that the muon, on average, would survive at rest, and that's the 2.20 microseconds. And over here, see that? That's an electron, that's a muon. You can't tell an electron from a muon, they just have exactly the same properties, the same spin properties, the same electric charge, except the muon is 200 times more mass. Okay, so it's a version of it. It's a heavier version of an electron. Other than that, everything just matches. So here is this beam of muons that we've produced. It turns out that the muons, are those velocities? I guess they're velocities. I'm trying to remember what I wrote. Muons decay into what are called neutrinos. So when muons decay, they end up producing a neutrino. They also produce electrons. So you'll get an electron and a couple neutrinos in the decay. And that's actually the symbol for the neutrino. So I'm trying to decide if I wanted this. These must just be the velocity vectors. So the velocities here is 0.60 c. The gamma factor I can calculate. So let's practice using this formula. With 0.6 c, I'm getting a gamma factor of 1.25. So it says that these muons are going to survive 1.25 times longer at this particular speed where we've generated them. So I can calculate the new lifetime for these rapidly moving muons as gamma times the proper lifetime, the lifetime they would have if they were at rest. So in the muon's own rest frame, you know, if the muon says, well, this is my rest frame, this is my inertial frame, and in their own inertial frame, it's always the 2.20 microseconds, right? Or that's the average lifetime. It's only when we're in a different reference frame where they're zipping past us where we get these effects. So it says in this frame, on average, they're going to live 2.75 microseconds. Now, how far are they going to travel? Well, since we're doing the measurement in this reference frame, we just have to know how fast they're traveling and how much time goes by. So we can put those numbers in. We can calculate the v. In fact, I think they calculated it, right? But we should be able to do that too. So we can take 0.6 times the speed of light. That will give us 1.80 times 10 to the 8th meters per second. And then multiply it by 2.75 microseconds, because that's how long they're going to live. And it turns out they can travel 495 meters on average before they decay. So again, here's a reminder of what that gamma function looks like. What else do we need here? Oh, I redid it. So what would happen if the speed of the muon, instead of 0.60, what if we generated a muon beam where the muons were going 0.999 times c? That's much faster. Well, at 0.999, the gamma factor there would be 22.4. They would survive, on average, 22.4 times longer. And at that, they would have a lifetime of 49.2 microseconds, and they would travel 14,750 meters on average. They would travel a long way, right, in that, during that time period. So they survive 22 times longer, and that's how far they could travel. Okay, so, you know, we're not making this stuff up. These are measurements that are routinely done in, say, particle accelerator laboratories. This really is the way things work. Let's do another example of, well, it says time dilation. So it says, what about 100 kilometers per hour? I've got this really fast car, and I can go 100 kilometers per hour in it, which is actually only about 60 miles an hour. How much time dilation will we get for this kind of everyday speed? A car traveling covers this, sorry. Okay, so let's try this example. What happens if we have a car going at some speed, 100 kilometers per hour, that works out to be 27.8 meters per second, no big deal. Well, let's see what gamma does. Well, what happens is the V here, the 27.8, it is tiny, 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 tiny. And C here is huge. C is 300 million. And when I plug those in my calculator, you guys can try this. When I take 27.8, divide by 3 times 10 to the 8th, and square it, my calculator says 0. Or else it starts flashing and says it can't, or it reports something back in scientific notation. Actually, let me back off there. So I think at this point the calculator goes to scientific notation, but it's something really, really tiny. And then when we take 1 and subtract that tiny number off, it reports back 1. What your calculator does is, it does its best, but calculators typically are designed so that they can only keep 10 digits of precision. And there's no way for your calculator to report the number, because the number in this case is going to be 1.000000000. There's going to be a lot of zeros, and then way out here are going to be some non-zero numbers. But the calculator can't fit that in the display, and so it doesn't show you the rest of it. So what we have to do is what are called approximation techniques. Now it turns out we can show, you don't have to worry about the details of this, if the speeds are really slow compared with the speed of light, which this automobile speed is, pretty much all of our everyday speeds are slow compared with the speed of light, then gamma can be approximated as 1 plus 1/2 v squared over c squared. What that says for this car traveling at 27.8 meters per second is that the gamma factor, so I wrote this out, this didn't come out of my calculator, it came out from using this formula right here. It says gamma is approximately 1 plus 1/2 v squared over c squared. Well, 1/2 v squared over c squared is 4.3 times 10 to the minus 15. So if I did write that out, if I had a display that would keep track of all those digits, it would look like 1.000000000000043. Okay, now I put commas in just so we could keep track of groups of digits. But you can see, for everyday kind of situations, the gamma factors are pretty much just 1. And so we don't measure length contraction. Very, very difficult to measure that in everyday situations. Time dilation, you really have to get some precision atomic clocks to be able to measure these very slight time variations for everyday objects. Now what's happening is, in the driver's time frame, when 10 seconds go by, we can use the time dilation approach and say if 10 seconds pass in the driver's reference, then an observer watching that driver go by would measure 10.0000043 seconds. Okay? And that's just too small of an effect for us to be readily measurable. So for relatively slow-moving objects, these are going to be difficult measurements to make, whereas with these high-speed particles, like these muons, no problem at all. We measure these in a laboratory, and we can easily measure that they're living for much, much longer, traveling much farther distances than we would expect if we didn't know about relativity. All right, here is kind of the traditional problem dealing with lengths and time effects, and that is space travel. It's been suggested that you could use a really, really high velocity spacecraft to travel far, far distances, and that the astronauts going along on that would actually not have very much time pass. So this is what it would look like. I'm going to jump ahead here. Let's put some numbers in and see what happens. So first of all, let's identify the reference frames that we're looking at. So in the in the reference frame, of the Earth and the distant planet, let's say that there's 20 light years of distance. Now, light years is a distance unit, but the way we can one way we can write those units down is to write it as a factor of c times a year. This turns out to be really convenient for solving problems using light years, so I highly recommend this approach for these kind of problems. So what's going to happen here is, let's say this. Let's say that the spacecraft is able to move at 95% of the speed of light. Now, just to be clear, that's a really high speed, and we just, at this point, have no idea how we would ever bring something up to a speed that large. But if we did, let's say we discover a propulsion system that enables us to bring that spacecraft up to a speed of 0.95 c, what would its gamma factor be? And we can solve for gamma, and we find out, we're going to get this 3.20 gamma factor in terms of distances and in terms of passage of time. So what we can do then is, let's move into the spacecraft reference frame. Now in the spacecraft reference frame, the spacecraft is at rest. And it's the Earth and the distant planet that are in motion. Now, the distance between the Earth and the distant planet is 20 light years in the reference frame of the Earth and the distant planet. This is like a really big meter stick. But in the reference frame of the spacecraft, it's like this really big meter stick is going by at 0.95 c, and as a result, there's going to be a length contraction. The length contraction applies to all of these distances that were measured in the reference frame of the Earth and the distant planet. One of those measurements was the 20 light year distance. So to find out how far is that distant planet, once the spacecraft is up to speed, that distant planet is only 6.25 light years away. Now that's still a pretty good distance, but it's gone from being 20 light years away to being 6.25. Now how much time then will pass inside that spacecraft on the way to the distant planet? Well, the distance is 6.25 light years, and the planet, now remember, we're in the spacecraft's reference frame, so as far as the spacecraft is concerned, they can consider themselves to be at rest. And then in their reference frame, what they see is a planet coming towards them, and the planet is coming towards them at 0.95 c. Now that says that we can take the distance, the planet is 6.25 light years away, and it's coming towards them at 0.95 c. I can write in the distance and the speed to calculate the time. Now the factor of c that's in the light years will cancel the factor of c that we have in the velocity. So the factors of c will go away. So when you calculate the velocities in your problems, typically what you want to do is leave the factor of c there. Okay, so leave the factor of c in place, because there's a good chance that that factor of c will cancel out farther along in the calculations. So the c's cancel out, and we run the numbers here, and the units that are left are years, and it says, given these values of distance and velocity, distance and velocity here, the time it's going to take is 6.6 years. So it's going to take 6.6 years for the astronauts to get out to that planet. Now that's in the spacecraft reference frame. So 6.6 years out, maybe they spend the weekend, and then they travel back. So 6.6 years out, 6.6 years back, that's 13.2 years that have gone by. So they come back to Earth. For them, traveling out and back, 13.2 years have gone by. Now let's go back to the Earth's reference system. In the Earth reference system, the distance was 20 light years. And so the amount of time that while the spacecraft traveled from Earth out to the distant planet, that's going to be given by 20 light years divided by 0.95 c. The factors of c cancel like before, and the amount of time that takes place on Earth and on the distant planet, they're both in the same reference frame, is 21.1 years. So that says 21.1 years out, that's 42 years have gone by. So on Earth, when the astronauts come back, 42.2 years have gone by, but the astronauts only, 42 years versus about 13 years. Okay. Now, that's the predictions from relativity, and we have every reason to expect that would, if we did build a spacecraft and followed all these speeds, that is what would happen, based on small effects that were met. We can measure these small effects. We can measure effects with satellites in orbit. We can put atomic clocks on just commercial airlines and measure differences in passage of time due to differences in gravitational field and due to the speeds of the planes. So these are measurable quantities now. So if we did ramp up to these extreme kind of speeds, we have every reason to expect that this is the way nature works. So that's kind of interesting. You can actually get differing amounts of time passage. And that's what it comes down to. First you might think, well, how is that possible? But you're saying how is that possible is based on the assumption that there is a universal clock and that the entire universe moves forward in time. The time passage is the same everywhere. And it turns out that's not true. It turns out that time passes, the passage of time, the time intervals between events depend on the gravitational field, what is the local gravitational potential that you are doing your measurements in, what's the gravitational field that you're in, and then the other item it depends on is how fast you're traveling. So those are the effects that determine passage of time. Okay. All right, here's an example. Now this is relativity due to a GPS satellite. So it says that GPS satellites, they're about 4,000 miles, their velocity is about 4,000 meters per second. So that's not super fast, but it's fast enough that we're going to have to use relativity calculations in order to make the GPS satellites. This is the global positioning system, right? So you get out your phone and you ask, where am I located? And the phone is getting information from satellites, and by measuring time delays of signals coming to you from a series of different satellites, the phone, you're able to do calculations, your phone's able to do a series of calculations and tell you where you are located to within a meter. Okay, so it can measure where you're located to, that's how good the global positioning satellite system is. And what it depends on is programmed into those GPS systems are formulas from special relativity, what we're studying here, and also general relativity. Now, special relativity deals with time differences due to speeds, and that's what we're looking at here, the 4,000 meters per second. General relativity says it's not just how fast you're going, but it's also the specific values of the gravitational field. So that's what we're talking about in these two parts here. So it says that we're using atomic clocks to measure these satellites that are in orbit. All they are is just precision clocks. And they are sending signals out, or they're internally keeping track of the passage of time within their reference frame. And then they send out signals at a regular interval. So here's Earth. Here's an example of one of those satellites. We can look at time dilation. Now we can still use the low speed approximation that we've used before for gamma. And it says that at 4,000 meters per second, the gamma factor will be 1.0000000000089. So that's really close to 1. But the GPS system is so precise, the timing information, that this amount of variation makes a difference. The GPS system satellites have to be programmed, or your phone has to be programmed with formulas like this from special relativity and formulas from general relativity. So the velocity here is 4,000 meters per second. The radius of the orbit for the GPS satellites, I guess they told us that in the problem, is at 25,000 kilometers, the radius of the orbit. Now, one day is just the passage of one day is 86,400 seconds. So during each day, how much difference in time would this gamma factor introduce? And this extra piece of the gamma factor, this 8.9 10 to the minus 11, this 1 part well, let's see, it's actually 100 parts per trillion. That turns out to be 7.7 microseconds every day. So the clocks, due to the motion of the satellite, the clock in the satellite and the precision clock on the surface of the Earth are going to differ by 7.7 microseconds per day. Okay, so that's the difference in passage of time between the two. Now the gravitational effect, there's also a gravitational gamma factor that we can relate to the mass of the Earth, the gravitational constant, a couple factors of c and the distance r. And if we do the same calculations to find out how much of a gravitational time dilation effect there is, that turns out to be at the surface of the Earth, the passage of time is slowed down by 7.1 parts per 10 to the 10th. For the satellite that's at a higher distance, it's at a higher distance in Earth's gravitational field, the gravitational field is not as large, and as a result, the time dilation factor there is significantly less. So what we can do is we can look at both of these effects. We can look at timing differences due to special relativity and due to general relativity, and it turns out that with this gravitational effect, that's working out to be 45.8 microseconds per day, but that's going to be longer. So the satellite, during the same time interval, 45.8 microseconds more time passes. We're deeper into the gravitational field, and as a result, the time dilation is time is not passing at quite the same rate. I don't know if you guys saw the movie Interstellar, where the spacecraft is traveling in and around near where there's a black hole with this really large gravitational field, and they're doing the calculations on how much, for them, time dilation is going to occur. And so for them on the spacecraft, very little time passes, but when they come out of that gravitational field, they're going to find that back home a lot of time has passed. Anyway, good movie. So for the satellite, there's a gravitational effect of 45.8 microseconds. There's a velocity effect of 7.7. The overall effect is that on the satellite, 38.1 microseconds more occur each day than on Earth. And that has to be taken into account in order for the satellites to enable us to maintain that high level of precision on the GPS. So yeah, this stuff is for real. It's built into the GPS systems that you use all the time just to figure out where you're located. All right, this is kind of a crazy example. It says here, I think, here is a portrait. It's at rest. It has a height of 1 meter. It has a length of 1.5 meter. What would happen if someone took this portrait, or this painting, sorry, and went by at a really high speed? So here is this, this really nice landscape painting, and what happens is the length contraction only takes place in the direction of motion. So if it's hung on the side of a spacecraft, okay, that makes the story more interesting. It's on the side of a spacecraft. The spacecraft goes by at so it's like an advertisement on the side of a spacecraft, and it's going by us, and it's going by at 0.90 C. How much contraction are we going to get? And the contraction is only going to occur along the length where the velocity is. And so V is equal to 0.90 C, plugging into our gamma formula. Gamma is 2.29. Now another item I guess I should point out here is that the velocities are given as some factor times C, then don't plug in 3 times 10 to the 8th. Chances are, in almost all situations, not every situation, but in most situations, if you're putting 3 times 10 to the 8th into your calculator, you're missing out on a shortcut calculation. So what we can do, since they gave us the velocity in terms of c, then we can just write down the number 0.9, and the c's will cancel. So this becomes 1 minus 0.9 squared, and then we take a square root, and then we invert that, and we get 2.29 as the gamma factor. So B doesn't change. So B will still be the 1 meter. But the A, since this is a factor of 2.29, A that was 1.50 is now length contracted to 0.654. Okay. And maybe our last, we got to check the time here. Maybe we've gotten to where it's time to take a break. Yeah, let's do that. So let's go ahead and take a break right there. If you guys have any questions, let me know.